This is a production of Cornell University.
Hello, and welcome to the Faculty Forum of the Cornell University CyberTower, uh, a monthly conversation with a faculty member at Cornell about an area in his or her expertise. I'm delighted today to have as my guest Professor Ken Hover, who is a professor of structural engineering in the College of Engineering, and who's going to talk a bit today about bridges, the materials that make them, and the state of American bridges. Kent, so nice to have you in today.
Thank you very much.
Uh, Ken, we're going to begin, I hope, by talking a bit about this bridge collapse in Minnesota. But I wonder if you could begin just by telling us a little bit about your own background and how you got interested in this
Okay.
field. You're an expert in materials, materials that go into roads and bridges and other structures. How'd that interest grow?
Okay. Well, I have a little bit of an unusual background for a faculty member. I started off with my bachelor's degree in civil engineering from the University of Cincinnati. And Cincinnati is one of the schools in the country that has a mandatory cooperative education program. So the bachelor's degree takes 5 years, and you end up alternating your academic quarters with work assignments. My first assignment was with a construction company. I ended up then actually staying with them full time for a number of years. I got my master's degree at night school while I was working for that construction company. I had worked my way up from an assistant cost estimator ultimately to project engineer of a bridge job, Interstate 471 bridge over the Ohio River between Cincinnati, Ohio and Newport, Kentucky. And that experience being one of my first major responsibilities right out of college, I think really set the tone of my interest. In some ways, that was an extraordinarily exciting opportunity.
Now, you were in the Army Corps of Engineers too, weren't you?
That's right. As everybody would recall, there were some strange things happening in the country in the early 70s relative to our military buildup for Vietnam, and then an immediate reduction in force. So even though I had been an ROTC student, the Army said, why don't you just go ahead and take a couple years, finish up that master's degree, and then report to active duty, which I did. So that after obtaining the Master of Science in Civil Engineering and after working on that bridge project, I then reported for duty with the Corps of Engineers.
Now, tell us a little bit about your teaching and research activities at Cornell as they involve structural engineering.
All right. In a typical year, I have three particular areas of responsibility in the classroom. One at the undergraduate level, teaching the design of reinforced concrete structures and masonry structures. At the graduate level, I teach about concrete materials, which really is a reflection of the fact that in my career, all of the projects that I've been assigned to working for the construction company were concrete projects. And then actually after the Army, when I switched and went to work for a structural design company, most of the jobs that I designed were concrete projects. So at the graduate level, I teach concrete materials, and in particular, the influence of materials, construction technique, and environmental conditions. The weather, is it raining? Is it hot weather? Is it cold weather? Is it dry air?
And how does that affect
And
the
how
structures
that influenced
themselves?
the quality of the material. And then I also teach in alternate years and introduction to construction management.
Okay, let's talk a bit about that bridge collapse. It occurred in Minnesota about a year ago,
Actually,
two
last
years
August.
ago,
Last August.
last August. It really focused our attention on the state, I think, of the American infrastructure generally. I want to ask you about that, the infrastructure in the United States, but did you have some direct involvement in the aftermath of that bridge collapse?
Okay. I have had some direct involvement in the aftermath of other bridge collapses, but not specifically with the I-35 bridge in Minnesota. It turns out that coincidentally, I do a lot of training for the Minnesota Department of Transportation. So I know a lot of the fine people who are involved in the work on that bridge and in the investigation afterwards, but I do not have a direct involvement or any specific information that any other professional engineer in the country would be able to glean from recent news reports and from our professional societies.
All right, let's step back and give us a kind of a snapshot, Ken, of our system, if we can call it that, of interstate bridges in the United States.
Okay, and I think system is the key word, and I think also we would both be sure that we would not want to use the event of that bridge collapse as an opportunity to discuss other things. There's certainly no discussion that we can have about the national infrastructure which would bring comfort to the people who are directly influenced by the tragedy of that collapse. But nevertheless, it does, as you say, focus our attention on the national infrastructure. And I brought a few figures to help us understand what we're talking about here. In the United States, we have some 4 million miles of public roads. 47,000 miles are in the interstate system itself, about 115,000 miles in other non-interstate highway. Now, within the U.S. federal system, including the interstate, there are 115,000 bridges. In the interstate system alone, there are 55,000 bridges. On average, there's about a bridge per mile for the interstate system. Now, just in the state of New York, within our own home state, to get a feel for the magnitude of the transportation system, there are 19,500 bridges in the Empire State. In New York City alone, there's 2,100 bridges. Just in Tompkins County, the home of Cornell University, there are 200 bridges. I think most of us on our way driving to and from work would not recognize that just within our own county, we're dealing with 200 bridges.
And of course, whenever there's a bridge collapse, Ken, people like me at least give some thought to some of those bridges as we cross them or as we approach them in some sense. Is there a way to generalize about the state of all of those bridges?
Yes, there is. Federal law mandates an inspection of all highway bridges at least every 2 years. And as a result of that inspection, a bridge is classified into one of three categories, which tells us what kind of attention to apply to that bridge. One category is known as structurally deficient. Now, lots of us would hear the term structurally deficient, and we would at first fear that the bridge, in fact, is in danger of collapse. But structurally deficient essentially means that this bridge has issues which require repair or attention. We have to schedule repair, we have to schedule maintenance for this bridge, but it does not mean that the bridge is in danger of imminent collapse. If any bridge inspector or any bridge engineer had the feeling that a bridge was in danger of collapse, they would then close the bridge immediately. So we don't have to worry that we have classified bridges as being deficient, and what that means is that
so if a bridge is categorized as structurally deficient, cars can still continue to cross that, and there's no substantive concern that there will be an accident?
That there is no reason, there is no data which has become available as of the time of that inspection that would indicate to us that the bridge could no longer perform its daily load carrying capacity. Now, one of the things that can happen with a structurally deficient bridge is if the evaluation of the inspection report tells us that we should not put as much load on the bridge, then we end up posting the bridge, and then you have signs on each side of the bridge and on the highways approaching the bridge that would limit the maximum load of trucks or limit the number of truck axles or the length of the trucks or the load that would be applied to that bridge. Now, to give you a handle on the magnitude of the issue, within this interstate system of some 55,000 bridges, about 16% of those are rated as being structurally deficient, which means that about 16% of our bridges require attention to be able to keep their load carrying capacity intact. Now, there's another category which is known as functionally obsolete. Now, this is another term which is potentially dangerous. The public hears that a particular bridge has been categorized as functionally obsolete. That would make one think that I have got to find a detour and go around that bridge. The term functionally obsolete means that this bridge, even though it may have full structural integrity and full structural capacity, cannot carry the volume of traffic that that bridge is currently experiencing. What that could mean is that the shoulders aren't wide enough, that one single traffic accident on that bridge would then end up clogging the bridge. It could mean that the approach or exit lanes to the bridge are unsatisfactory to be able to move the intended flow of traffic across the bridge.
All right, now when you say cannot carry, what do you mean?
Just physically, the bridge is either not wide enough, or the traffic cannot cross the bridge at an adequate speed because the bridge essentially is a bottleneck in the transportation system.
So what would happen if it got that categorization, functionally obsolete?
How that would manifest itself to the public is that there is a delay in crossing that bridge because we've got multiple high-speed lanes that are now condensing down to a bridge which is narrower than it should be. Like I say, if it doesn't have adequate shoulders, then all it takes is one fender bender accident to clog the bridge. So functionally obsolete does not refer to load carrying capacity in the terms of weight or gravity. It refers to load carrying capacity in terms of the volume of traffic flow that needs to go over it. Now, when we talk about the functionally obsolete category, within the interstate system, about 12% of the bridges are classified as functionally obsolete. Now, we add that to the 16%, and all of a sudden we're looking at 28% of the bridges on the interstate system, which for either a structural load capacity reason or for volume of flow, they are not performing the mission that we need them to perform right at this instant. Now, within the state of New York, about 12% of our New York bridges are classified as structurally deficient, and 26% are classified as functionally
Now that
obsolete.
seems like a lot to me, Ken.
That is a lot, but we have to keep in mind that the structural deficiency means that we have identified an issue with that structure, and that we are going to be monitoring that issue. The inspectors know exactly what to look for when they come out, that maintenance is scheduled for that bridge, repairs, if necessary, are scheduled for the bridge. Let's also keep in mind here, there's a big difference between structurally deficient and not able to carry the load. Once again, if any inspector or engineer determines that that bridge cannot carry the load, that bridge will then be closed. So we will not be driving over bridges which are knowingly risky.
If a bridge is declared structurally deficient or functionally obsolete, does it automatically get on a queue or a line so that that condition is repaired? I mean, there seems here to be a backlog. If we're talking in New York about 40% of the bridges in need of some kind of attention, that sounds to me like a long backlog. And is that largely a function of state budgets?
State budgets and federal budgets. You are exactly right about the backlog. In fact, a few years ago, there was a report released that said that our national backlog for bridge upgrade was in the range of $32 billion. If we throw about $3.5 billion at that per year, the best we can do is just maintain a $32 billion backlog. We would have to ratchet up our annual average bridge upgrading budget to a little over $5 billion per year just to be able to take that backlog and reduce it to zero over a 20-year time period. So there's no question about it. There is a very significant maintenance backlog in our national highway system.
Now, we've left out one category of problem with bridges. Why don't you talk about that a little bit?
Okay. The other very interesting category of bridges are those which are flagged as fracture critical. Now, this does not indicate that there is any current problem with that particular structure. What the fracture critical category does indicate is that one or more components within that bridge have been identified such that the loss of a single component would then very significantly jeopardize the load carrying capacity of the structure as a whole. Now, we have many bridges which are in perfect condition and are carrying their load, but the nature of the design means that one particular connection, one particular steel member, one particular concrete member could cause a significant problem with that bridge. I'm quite familiar with the way the New York State Department of Transportation manages these things, and once a bridge has been identified as fracture critical, then first of all, the cause, whatever element seems to be the vulnerable one in that particular case, is very clearly identified. And then that bridge is scheduled for more frequent inspections. And when the bridge receives those more frequent inspections, extra attention is applied to those elements which are the ones which could trigger significant.
And does that one get to the top of the queue?
It moves to the top of the queue very quickly. Now, interesting discussion point would be, I've identified a fracture critical bridge over here, which seems to be in perfect condition. It is not exhibiting any corrosion problems, any deterioration problems. It is carrying its load quite satisfactory. Now, I have another bridge over here which is not classified as fracture critical, but general purpose corrosion, deterioration, and the increased growth of cracks due to large numbers of traffic loads is causing this one to now be somewhat more in jeopardy. So the folks who have to make these decisions have some very difficult debates about which is the better place to put the limited money that's available.
Yeah. Now, I have to tell you that I find the language used to characterize these bridges kind of scary. Deficient, fracture, critical. Do these terms reach the public? In other words, if I'm driving around, do I have any way of knowing whether any of my bridges in our little Tompkins County have been categorized in this way? Or is this an internal categorization?
It is an internal categorization, but there is no effort to shield the public from these terms. For example, you can go to the website from the American Association of State Highway and Transportation Officials, AASHTO, and you'll find these terms clearly listed, and you can click on your home state and you can find the inventory for every state. You can go to the state, you can go to the county, and you can go to the inventory for that particular county. You could look up those 200 bridges in Tompkins County and you can find that. Now, on the other hand, would you as an ordinary driver be able to identify that? Unless you saw signs that said that the load capacity of the bridge that you're approaching has been reduced, unless you saw signs that directed trucks that had axle loads in excess of some particular weight to take a detour,
you wouldn't know.
No, you would not know.
You wouldn't know.
No.
So the only way you could know, presumably, was to go to the website and check out. I'm going someplace. I can look up any of the bridges I'm going to cross just to know. And do you recommend that?
No, I would not necessarily. I would not necessarily recommend that. I don't think that would give you much in the way of additional information. So
it'd probably scare you, and
it could scare you. In fact, your reaction to these terms is interesting, and I share a similar reaction. The term structurally deficient, and then we have to go to the official definition to say, well, that doesn't sound quite so bad. And we talk about fracture critical, which does not mean it's cracked, doesn't mean it has a critical crack. It just means it's vulnerable to a crack. I think in some cases these terms might induce more concern in the public than is necessary. But on the other hand, were the bridge agencies, were the public agencies to change those terms and tone them down a little bit, I think one could accuse them of trying to spin.
Yeah, no, you're right. I mean, I think once you're in it, it's hard to get out of it.
Yeah.
But language is, I think you engineers may need some English professors, you know what I mean, to lend you a hand
Always.
A little bit in some of that language.
It could be.
Let's return for a moment to the bridge in Minnesota,
Sure.
Ken, if we can. Now, you're an expert in the concrete as a material and in concrete structures. Was that a concrete bridge?
No, the superstructure of that bridge, the supporting structure that carried that bridge over the gorge and over the river, was made of structural steel, and then the deck, the roadway, was made out of concrete. Very, very common construction combination in the United States.
And do we know much about what caused the Minnesota bridge to collapse?
Some information is beginning to come out. The National Transportation Safety Board has, of course, immediately begun inspection, and they brought in some pretty high-power experts to begin to do the analysis. And just as when we have catastrophes such as plane crashes, they retrieve as much of the debris and damaged structure as is possible, remove that to a safe location so they can study it. Just a couple weeks ago, a preliminary report was released, and of course, we all have to be real careful about jumping to conclusions on the basis of preliminary reports. But the early information indicates that the investigators are beginning to focus their attention on the connections among several structural steel members. You know, we bring individual steel bars and steel sections together, and lots of times there isn't physical room on the end of a single piece of steel to be able to connect all the bolts and all the nuts that are necessary, particularly if 2 or 3 members are all coming together in one point. So we then create a piece of structural plate, which is known as a gusset plate, and that each of the individual members are then connected to that gusset plate. The gusset plate essentially just gives us room to be able to bring all these members together. And attention seems to be focusing on the gusset plates.
When bridges are inspected, are those gusset plates inspected? Is there any way of gauging the current state of those gusset plates?
Absolutely. In fact, one of the tremendous advantage of bridges which are built out of structural steel is that almost always the individual structural elements are available for direct visual inspection. And it would be absolutely routine to inspect all of those connections, just like you would inspect the nuts and the bolts and the washers and the welds. It actually becomes a bit more difficult when the bridge is made out of reinforced concrete, because the reinforcing steel elements are in fact encased inside of concrete, so that it is much more difficult to peer inside and see what's going on.
So how does it happen, Ken, that here's a bridge in Minnesota? There's I'm sure, a schedule of inspections in Minnesota as in
Absolutely.
other states. Do we assume that the kind of inspections we have should fairly routinely identify these problems? Is it that somebody maybe just missed it, or that
No, the draft report that I've seen so far, and keep in mind this is preliminary and this is a short form report, does not suggest to me that there had been a long-term problem with the connections. I have not seen any evidence that there was damage that could have been detected prior to the bridge event of this last summer.
so how could that be?
They have identified what they believe may be a vulnerability to the connections, which may not have led to a problem until this summer. But there's still a lot of investigation which is going to happen, and I'm sure the final report will be reviewed by many other parties. So we have to wait and see what the actual results are.
So my layman question to you is that I think of bridges, or the elements of bridges, or the connections in bridges, deteriorating over time in a way that's detectable, a kind of gradual deterioration. Does this suggest that there can be what I'm going to call a catastrophic deterioration? In other words, a deterioration that occurs over such a short span of time that it wouldn't be caught in the cycle of inspections?
That is entirely possible. In the general case, our design philosophies are such that if a problem develops with a structure, we want that structure to then begin to move and to yield and deform. We want cracks to grow in a controlled manner. Recognize the life of a crack. It begins as a microscopic gap between pieces of the material, and it eventually grows to a place where it may be detectable if you have magnification. It then grows to the place where it is visible to the human eye, and then at some time after that, it grows to the case where the member can maybe no longer perform its particular function. we intend to design our structures in a manner that there is a detectable
Yeah,
sequence. I would also have to say that that is not
doesn't always
always the
happen. It
case.
doesn't always happen
A
that way.
crack can be very small today and very large tomorrow. Many of the viewers have experienced a crack in their car windshield, and that crack was a very small one, and then they come back after a little while and they see that the crack is longer. Now, glass is a very brittle material, and cracks grow very rapidly in glass. I just use that as an example of the fact that cracks can grow rapidly.
Yeah. But you're as a structural engineer, you and your colleagues are actually have the detectability of problems in your radar screen as you're designing
Oh,
these kinds of things.
there's no question example. For example, one of my colleagues is Professor Tony Ingraffia. He is an internationally known specialist in cracks and crack growth in not only materials like concrete and ceramics, but also in steel and particularly in aluminum. And crack growth in aluminum, such as in airframes, is a critical issue. And one of the things that Tony specializes in is understanding how rapidly cracks grow and how large can they be before we can detect them, how much longer can we use the structure after a crack is identified, and that sort of thing. So the field, the subfield of structural engineering, which is known as fracture mechanics, is an area which is covered in great depth in our department at Cornell.
So, stepping back, you talked about the three kinds of problems with bridges, and you talked a bit about the how many bridges were in each category. I'm a citizen. I'm in touch with my state assemblyman, my state senator, my congressman. Uh, do you have some sense of urgency about what ought to be done to restore the system or to make the system so that either these percentages go down? Are these percentages high enough to alarm you that there needs to be some intervention now? I think people would like to know how nervous are you, or how anxious are you about the nature of this system?
Okay. Well, I think if we go back to the definition of those classification terms, the term structurally deficient essentially says intervention is required on this bridge. Now, intervention does not necessarily mean propping it up and shoring it up or closing it. Intervention can mean we have got to schedule maintenance, we have got to make repairs, we've got to replace some key elements. So I think just the existence of bridges that are in the category of structurally deficient means that intervention is required. Just the existence of a $32 billion maintenance and upgrade backlog says yes, we have to do something, and the $3 or so billion per year merely holds us at that level of backlog. I think there's no question that all of us, whether or not we are structural engineers, would say what we want to see is we would like to push those percentages of structurally deficient and functionally obsolete to near zero. We would also like to be moving fracture critical structures off of the inventory. We are no longer building structures which are classified as fracture critical. We're building redundancy into the system. We are recognizing, particularly in this modern age of international events, that any unexpected event could occur at any moment. And we would like to have our structures to be able to survive these events.
Do you have a sense, Ken, that here we are in the 21st century? Is our infrastructure in the same shape, better shape, worse shape than it was 20 years ago, 30 years ago? Is it possible to draw a conclusion about that?
I think we can draw some general conclusions. If we were to move the clock back 40 years or so, when the interstate system as a whole was much newer, we would then be in a very different
Sure.
Basis of comparison. Actually, it turns out that over the last few years, we have been able to take these structurally deficient numbers and inch them downwards. They're actually lower now
Oh,
than
they
they were
are.
2 or 3 years ago.
Okay.
So some progress is being made. There is absolutely no question about that. But another interesting statistic is when we look at those 55,000 bridges just on the interstate system alone, um, more than 80% of them are now more than 25 years old.
Yeah.
So what that is saying is we've got a very large bridge inventory out there. Almost 20% of them go back to the 1950s. 44% of them go back to the 1960s.
So it's an aging
So
infrastructure.
it's an aging infrastructure. There are a very large number of bridges that are in the same general age era as the one that went down in Minnesota.
All right, so walk us through some of the challenges and opportunities. Ken, let's start with inspection.
Okay. Back in 1987, the Schoharie Creek Bridge collapsed here in New York State on the New York State Thruway. As a result of that, the governor convened what he called the Bridge Safety Assurance Task Force, and I was a member of that to represent concrete structures. There were a couple steel structure specialists, a couple hydraulic specialists, a federal system specialist, and a record keeping specialist. And we toured the state to take a look at inspection procedures, the next process, which is the evaluation of inspection data to determine what the condition of the bridge is going to be. And that was an absolute eye-opening experience for me. It is extraordinarily difficult and it is dangerous to inspect a bridge. We don't normally close bridges while we inspect them.
Yeah.
So we have got bridge inspectors who in many cases are hanging from rappelling ropes. They are using rock climbing techniques. They are using spelunking techniques to crawl along the way in bridges, which in many cases the bridge structure itself is covered in grime and debris, and they have got to shave all that away. They need high intensity artificial light to see what's going on. And after they do all that, they've got to figure out what it is we're looking at and what is the condition of the bridge. So that is just a physically difficult job. It's also logistically virtually impossible to inspect every member of every single bridge. You can't inspect every nut and every bolt. You cannot x-ray every weld. You cannot tap on every single member. If we have got to take the inspection force and get out there and visit every bridge every 2 years, it's got to be done pretty quickly. So how we take dangerous, dirty conditions, we take experienced people, put them out there and require that they move through that bridge briskly enough that they can get to the next one, that is a real challenge. So clearly one of the challenges is, are there technologies available to do more thorough inspection? Can we see more deeply into the member? In the case of reinforced concrete, we may have steel which is corroding, but it's embedded inside the concrete, so we do not get a direct visual indication of what's going on. So we have to use a variety of electronic technologies to see that.
So are there increasingly, Ken, are there, if I can put it this way, non-human techniques that are more accurate than having an inspector actually do the spelunking and climbing about?
Well, I think the key issue there is it more accurate? I was involved in a head-to-head test between a very interesting piece of acoustic technology which moved along a bridge deck and tapped on it with ultrasonic pulses and used that information to determine the integrity of the concrete underneath the roadway. And I compared that with a human operator doing a very similar test, tapping on the concrete and using the human ear to discern what was going on. And in many cases, the human ear, when connected to the human brain, was just an extraordinarily accurate sensor.
Yeah.
It was actually better. But the machine could move faster. The machine could record its own findings as it went. So what happened then, and this happens in many of these similar types of technologies, you use the non-human inspection technology to identify areas that may be questionable, and then you bring the human to that area for the
closer
That's right,
inspection.
for the closer inspection.
Okay, now let's talk about design of bridges and talk a little bit about some new structural forms, new materials, some things that are happening that you're involved with, that others are involved with, that will improve the design of bridges.
Okay, all right. let me refer to the notes here again a little bit. First of all, we use the word system. So there's kind of two levels of bridge design that we could think about. We could think about the design of a specific structure by itself. And then we also have to think about analyzing the entire transportation system. For example, with 55,000 bridges just in the interstate system alone, which is less than half of the bridges in the country. If we were able to develop techniques which would give us 99.99% reliability of our inspection and classification techniques, that would still mean that we would have to be prepared for possibility of 5 bridges that we somehow missed. Okay, so the magnitude of the system is important. So therefore, there is real system thinking which has to be brought to bear. So sometimes we engineers can get so lost in the details that we forget the overall system, and we have to create a robust transportation system for the U.S. And this is one of the areas in which the Cornell School of Civil Engineering truly specializes. We have got transportation system specialists on the faculty, and then just within our own structural engineering group, we have got several folks who specialize in the reliability of structures. They specialize in how can we make decisions when we don't get as much input data as we would really like to have. And certainly Mircea Grigoriou and Steve Koutsarlakis, that's their specialty. And let's look at the big picture. We got lots and parts and pieces.
I want to come back to materials in just a minute, but let me interject. Ken, you were telling me earlier something about this is my term, not your term, about the subjectivity of the standards that are sometimes set by the state for safety, the amount of snow that a structure might have to carry, and that you've been involved in some of those discussions where standards are set in some way, and engineers don't agree all the time about what'll make some. Talk about that a little bit.
All right. For example, we could put any particular technical topic on the table, and we could bring to that table a number of engineers, and each of them would have very intelligent and very rational opinions about how to approach the problem. But the more complicated the problem, the more those opinions would vary. When it comes to something like the public infrastructure, we have to set at least some minimum standards and say, look, we're going to expose the structure to at least this much load. If the design engineer has reason to believe that we ought to increase that load, then do so. And when we were having that discussion about snow, one of the things that is interesting is within the state of New York, we have a statewide building code. And in the general case, the state of New York building code follows the policies of what's known as the International Building Code, which is used as a model for most of the other states. But the state of New York recognized that the national model for the weight of snow that is applied to structures is not as accurate for New York State as our state code council believes. So they actually then adopted snow load regulations that were proposed by the Cornell College of Agriculture
and are they
and Life
more
Sciences.
rigorous or less rigorous?
In some cases, they're actually less rigorous.
They're a little less rigorous.
The understanding was that the Cornell Cal study of snow load over the state of New York was actually more accurate and was done on the basis of more comprehensive data. So that's actually one example of how work up here on the Hill ultimately can filter down to our laws and regulations.
Yeah. Now, what about the new materials? I mean, again, a layman like me thinks, oh, come on, concrete is concrete. But it isn't, is it?
No.
It's changing all the time, right? And how is it changing? And how do you and your colleagues experiment with different forms of concrete that might be more durable, stronger? Are those the criteria that you're looking for?
Absolutely. You know, a common misconception about the material concrete is that it is a solid material. We talk about things being as solid as concrete. A material which is truly as solid as concrete is about 60% solid, 40% empty internal pore space. It is an extraordinarily sponge-like material, but the trouble is the pores in the sponge are so small that the human eye can't detect it. But as soon as you spill water or as soon as you spill motor oil on your driveway at home, you recognize, you know how absorbent it is, you know how hard it is to get it out. And concrete will likewise absorb the salt water that comes from the application of de-icing salts in the wintertime. It absorbs oxygen, it absorbs carbon dioxide, and the combination of carbon dioxide, oxygen, and salt water then sponsors the corrosion of the reinforcing, which is down inside the concrete. So one of the keys to making concrete that will last longer is to find ways to create a material that has a reduced porosity, and that certainly is one of the things that we work a lot on at Cornell. One of the beautiful synergisms is that by the addition of the ash that you get from burning coal in a power plant like the one up the lake here, the addition of ash to the concrete will actually fill some of those pores. So if you get the right proportion of Portland cement powder and the ash, and then some other industrial products such as the byproduct of the manufacture of silicon for the computer industry, you blend those together and you can create a much denser, much less permeable, much less absorptive concrete. In fact, the most recent bridges that were cast down here in the Ithaca Octopus used a very high power mixture that was developed in Albany.
So your sense is that, not your sense, you're telling us that the concrete is getting better and better, more durable, a better and better material.
What I'll say is we, without question, have the ability to produce a superior concrete today. Now, the question is, do we do that routinely? Do we write construction specifications which are demanding enough to require that the concrete producer and the contractor give us that? But there's no question about it. In fact, making a more durable concrete that will last certainly 30 years easy, 50 years probably is no longer a research laboratory issue only.
And is that material also environmentally more sound?
It certainly can be. Anytime we use waste products like coal ash, which would otherwise go to a landfill, instead find value-added ways to incorporate that into the concrete, that is a win-win all the way around. When you manufacture Portland cement, you need a lot of heat energy to convert limestone and shale and clay into this chemically active powder. So we can cut back on the energy demand of the product by cutting back on Portland cement and adding fly ash. So that's just one example of how we get an environmental benefit and we produce a superior product.
So it sounds like you're feeling that that progress is being made not only in the design of materials, but that our infrastructure, perhaps not as quickly as you'd like it, is being attended to in a way that can give a sense of security to those Cornellians who are watching us speak today.
I would say there's no question that these developments are happening. Things are getting better. The percentages are coming down. Some of us might be somewhat impatient. We would like to see faster advances in the industry. We'd like to see the percentages of deficient bridges coming down more rapidly. But that price tag is looming out there. None of the newer materials which have been proposed and demonstrated to be effective cost less than our traditional method. They certainly cost more. A classic example is we would love to use fiber reinforced plastics in lieu of metals, or in some cases in lieu of concrete for our bridges. Here we have a material which is not going to care about de-icing salt in the wintertime. It's not going to respond negatively to absorption of oxygen or carbon dioxide. And there have been many laboratory studies and a good number of full-scale studies of the use of carbon fiber reinforced plastics, fiber reinforced polymers of all sorts. In fact, just a few years ago, Tony Ingraffia mentored a Cornell undergraduate student project in which they built a plastic bridge, a fully functional plastic footbridge. that material has still got a few engineering issues that have to be dealt with, but that's not nearly as difficult as dealing with the fact that it is a significantly more expensive
Yeah.
product.
So that's certainly going to be the challenge for our politicians in the decades to come, and that is the funding of both repairs and new additions to this infrastructure. And Ken, you've really enlightened us today, and I promise you we won't wait for a bridge collapse before bringing you in to give us an update on how things are going. Thanks so much for coming in
Thank
today.
you very much. My pleasure.